Good morning. Before I start, I want to thank the Vice President of Research, Maria, and she has always supported me, particularly in this experiment. And I also am very happy to see my good friend Dr. Daw and his family to come to this meeting. And what I would like to do today is to describe with you a little bit about the alpha magnetic spectrometer on the International Space Station. To realize the science on the International Space Station, you just have to remember there are only two kinds of cosmic rays in space: neutral cosmic ray, light rays and neutrinos, and this has been studied by many satellites. Then there's a charged cosmic ray. Charged cosmic rays have a mass. Because they have a mass, they are absorbed by 50 miles of Earth's atmosphere, which is equal to 10 meters of water. So to study intrinsic properties of charged cosmic ray require a detector above Earth's atmosphere. To measure their charge and momentum require a magnetic spectrometer in space. So AMS on the space station is the only way to provide long-term precision measurement of charged cosmic rays. This is an MIT-led international collaboration. The detector were constructed in Europe and Asia and assembled at the European Organization for Nuclear Research in Geneva. In last year, 3 universities joined us: Moscow Engineering Physics Institute, University of Kiel in Germany, and University of Oulu inside Arctic Circle. The 600 AMS physicists had worked together on accelerator experiment. None of us has any experience in space. So let me share you some example of previous work in Germany, and that is one of them is the detecting of elusive gluons, and a little detector only weighs 1,000 tons. And what is gluon? In nature, there's gravitational force, there's carrier we still do not know, electromagnetic force, like your cell phone, is transmitted by photons. Weak force is the collapsing of stars, the decay of nucleus is by Z and W. Nuclear force is carried by gluons. So this is a somewhat important discovery. One of the authors, at that time graduate student, Joe Paradiso, who is here today. Another experiment is done at the European Organization for Nuclear Research, known as the L3 experiment. In that experiment, we found in the universe there are only 3 types of electrons. Electrons we're familiar with, electrons from space, 200 times heavier, and electrons in the nucleus, 4,000 times heavier. There are 6 types of quarks, but more important, electrons and quarks have no size. Their radius is less than 10 to the minus 17 centimeter. If you think about it, you use electricity all the time. You never seem to be able to measure the size of the electron. Unfortunately, the results are in excellent agreement with the theory. When experiment agree with theory, what you learn is very limited. When the experiment confront the theory, you learn something more. So this was the experiment in the 16-mile circumference lab accelerator, and this experiment is not for space. The magnet is 10,000 tons, 6 stories high, and there are 300 tons of uranium detector, and this both from Soviet Union. It was the largest Soviet collaboration outside. So with this background, so when we started the experiment, I got this cartoon. shows my qualifications. So before I mention, there are many, before us, there are many pioneering MIT space program. One was led by our Vice President for Research, Greer, and then Voyager, Chandra, and many, many experiments. AMS is a space version of a precision detector used in accelerators. So on top, there's a transition radiation detector, 8 layers of silicon tracker, electromagnetic calorimeter, 2 banks of time of flight counter, a magnet, a ring imaging trunk of counter. In total, there are 300,000 channels of electronics, 650 fast microprocessors. It's not too big. It's 5 meter by 4 meter by 3 meter, not too heavy, 7.5 tons. So the signature of different particles and nuclei as they pass through AMS, the electron will leave this trace, proton leave a different trace, ion different trace. Cosmic rays are defined by their energy in giga-electron volt, momentum, charge. Charge is the location on the periodic table. For helium, charge equal to 2. And a new term called rigidity, meaning momentum per unit charge. Before we sent to space, the detector was extensively calibrated at the 27-kilometer LHC accelerator, and there you can see or measure data, and our simulation agrees to 5 orders of magnitude, meaning we understand the detector. This is very important because once you send the experiment to space, you can no longer send a graduate student to repair it. Halfway through the detector construction, NASA decided to get rid of us. And so this was a New York Times article. The long-awaited cosmic ray detector may be shelved. But many people have different opinion. George Smoot, Barry Barish, and others said, no, this is wrong. And also in the Washington Post, Steve Weinberg also said, this is not correct. And I received many visits. One of the ones that gave me the deepest impression was Steve Hawking, and he came with 11 nurses. And finally, the Congress, the House and Senate in 2008 passed a law to add additional flight to deliver alpha magnetic spectrometer to the International Space Station. After that, many people continue to visit us. I remember him spend the whole afternoon with us and try to understand the new technologies we develop for space. And after that, I decided to be more friendly to NASA. And so this is my support of the shuttle commander, Mark Kelly, who is now running to be a senator. I hope he succeeds. He's an awfully nice person. That's me. And so it was launched into space on May 16, 2011, and 2 MIT alumni, Michael Fink and Greg Chermatoff, Dr. Dole, remember certainly him. So in 8 years, over 135 billion cosmic rays has been measured by AMS. So let me share you some of the latest results. First is the origin of cosmic positrons. There are 3 sources of positrons. You have explosion of stars, produce protons and helium. When they travel through space, interact with other protons and helium, produce positrons from collisions. If you have dark matter, when they collide, they produce positrons. And you have a new astrophysics sources, unknown one, such as pulsar, will produce positrons. So there are 3 sources. because the great interest of positrons and electrons, before AMS, there were many, many measurements. And this is electron spectrum, this is positron spectrum. Looking at this spectrum, you notice the data not exactly agree with each other, has very large errors. When the data has large errors, it's very good for theoretical physicists because you can make many theories. And most physicists assume that the flux is equal to a constant times the energy to the gamma's power. Gamma is known as the spectral index. So this is called the power law energy dependence. Our measurement based on 1.9 million positrons, and this is our measurement. And this is, everybody believes positrons come from collision. And this explains the low energy part and what happened to this. Cannot be explained by existing theory. And so we finally found out the positron spectrum is a sum of a low energy part from collision of cosmic rays, another is a new source or a new astrophysics source or from dark matter. The most important thing is when you fit this to any formula, you have a cutoff energy, 1 over exponential 1 over ES, meaning after a certain energy, you're no longer going to see positrons. And that is a very peculiar effect. So at low energy, the data come from collision of cosmic rays. At high energy, it's from a new source or from dark matter, but has energy cutoff. Indeed, now we sit there for days and we don't see any more positrons at high energies. Another very curious thing, which I forgot to report to Maria last time, and that is antiprotons and positrons have exactly similar behavior. Antiprotons are a very rare object in space, and it goes up and tends to be flat. For electrons, this is based on 28 million events, spectrum goes up, goes down. If you analyze more carefully, you will see it comes from 2 power laws. One called power law A, one called power law B. What does this mean? It means a low energy, the contribution of cosmic ray collision, this is the green part, cannot explain the measured data. And this is different from positrons. A positron, you remember, a low energy positron can come from collision. But for electron, it cannot. It can only be described by a power law. At high energies, electrons do not have a source term nor a cutoff, and positron has both. Therefore, electrons and positrons are totally different. Electron, you can continue to measure the high energy. Positron, after a certain energy, it disappears. Now let me share some results with you on cosmic nuclei. There are 2 types of cosmic rays. One is called primary cosmic ray, proton, helium, carbon, oxygen, and so forth. They are produced during the lifetime of stars and then accelerated by the explosion of stars. Another type is called secondary cosmic ray, lithium, beryllium, boron. They are produced by the collision of primary cosmic ray with the interstellar medium. So there are 2 kinds. Now, what is the difference between these 2? First, let me talk about protons. This is the measured proton data for many, many experiments before AMS, and the data, again, do not agree with each other, has very large errors. So traditionally, physicists assume the flux is still constant times energy to the gamma's power. This is our measurement proton, the red point, based on 300 million protons. At low energies, it does agree with traditional assumption, traditional theory, but above this energy, you have unexpected increase, meaning the theory is no longer correct. So the proton flux cannot be described by a single power law. Before AMS, there were many results on primary cosmic rays. helium, carbon, oxygen, from balloons and satellite experiments. If you group them together, you have a random pattern, and you do not know what is going on, mainly because the error is so large. This is our measurement, above 60 GeV. 60 GeV, the primary cosmic rays have identical rigidity dependence for helium, for carbon, for oxygen. And you have one energy dependence, another energy dependence. They deviate exactly at this point. This is very strange. Cosmic rays are totally different things, but their energy dependence are exactly the same. Then there are secondary cosmic rays. Lithium, beryllium, boron also have identical rigidity dependence. This is lithium, beryllium, boron, and they are different from primary cosmic rays. Therefore, in space, all the cosmic rays across the periodic table have only two classes. And think that's unthinkable such a thing could happen. And so let me mention what we're going to do on the space station until 2024. That's the lifetime, projected lifetime of space station. One is complex antimatter, like anti-helium, anti-carbon, anti-oxygen, and then try to pin down the origin of positrons, electrons, and antiprotons, precision study of solar physics, and continuous study of heavy nuclei. Let me share with you some thoughts about complex antimatter. The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning, because before the Big Bang, it's vacuum, nothing exists, so at the beginning, it must be equal amount of matter and antimatter. This experiment is orders of magnitude more sensitive than previous experiment to look for antimatter from balloons and satellites. This is an antimatter candidate. This is measure the track in the bending plane, in the non-bending plane, looking from the top, measure the velocity. This signal has a charge -2. The mass is exactly the same as helium. Helium, of course, charge is +2. So you just begin to see antimatter. Such a thing cannot be produced from cosmic ray collision. The rate in AMS for anti-helium candidate is less than 1 in 100 million helium. At this extremely low rate, more data is required to further check the origin of this event. 1 in 100 million is a very, very small number. You absolutely must make sure it's correct. And anyway, nobody is foolish enough to put another magnetic spectrometer in space for the next 20 to 30 years. So we have time to check this. And the next question is, what's the origin of positrons, electrons, and antiproton? Today, we know at high energies, the positrons has energy cut off, and we do not know if it is from a new source or from dark matter. A new source and dark matter I will explain. The question is, what is the new source? Why do positrons vanish at high energy? The red point are the data we have now, and the green one will continue to take data to 2024. What is most important is to go to very high energy data. A new source could be pulsars. Pulsars emit light, and the light interact with the pulsar magnetic field, produce positrons to high energies, and it's continuous without energy cutoff. A light ray do not produce antiprotons. Antiproton cannot come from pulsars. So this is the projected antiproton spectrum. This is what we measured and extended to 2024, compared with the positron to 2024. Such a spectrum cannot come from pulsars, because pulsars do not produce antiproton, because a photon doesn't produce proton antiproton. Then what is dark matter? Remember your high school physics. If you have a galaxy, and you have a region of observable mass, and then you have, at a distance r, you have a star rotating in a closed orbit. A closed orbit means the force on the star is zero. That means gravitational force and centrifugal force must be balanced. And therefore, you can calculate the velocity of this star must equal to m of r, the total mass inside, divided by r. And so this curve will be from gravitation, assuming all the mass you can see. And this is the measured curve of a galaxy. That means there's a large radial mass you cannot see. So the existence of dark matter is not in doubt. What is dark matter? Collision of dark matter produces positrons, antiprotons. Dark matter particle has a mass m, and they move slowly. Therefore, collision of two particles produces a total energy of 2m. So dark matter collision produces antiprotons and positrons. So conservation of energy momentum requires positron antiproton energy must be smaller than m, and therefore there's a sharp drop-off at the mass of m. That's a unique signature for dark matter. So this is the red point, is our measurement, and this is a dark matter model. You see a sharp drop-off, but the error is still very large. Even though it's a good fit, you cannot say you have seen dark matter. You need to see this point in order to make sure it drop off. And this is why it's so important to go to this point. Then the next question, why are electrons so different from positrons? We do not know. All we can do is continue to collect data to higher energy to see whether there are any trace of similarity. Next item is study of solar physics over the entire solar cycle of more than 11 years. High-energy cosmic ray goes through the solar sphere and passes through quickly. Low-energy cosmic rays are trapped in solar magnetic field, so spin for a long time. This is some very new data we observe identical monthly time variation of protons and helium flux. And this is from May 2011 to May 2017. You notice where the absolute value is different, the change is exactly the same. And the question is, what happened over 11 years? In addition, a new surprise is not only monthly, but daily. The flux goes up and down. For proton and helium, it's exactly the same way. This is a phenomenon nobody predicts and nobody can provide an explanation. Not only that, we see proton and carbon varies the same way, and proton and oxygen varies the same way. The observation of carbon and oxygen vary with daily variation. It's a new phenomenon. And then also we see structures and positrons and electrons. And this again from 2011 to 2017. And this is the period where the solar magnetic field flips. And you notice before the field flip, after the field flip, the spectrum are very different, but the spectrum varies the same way. And the question is, after 11 years, does they come back? Next item are heavy nuclei. I've analyzed the first 8 elements. Now we're in the progress to analyze all of them. So let me share with you some very basic physics of heavy nuclei, namely properties of primary cosmic rays. Light elements, helium, carbon, ion, are produced during the lifetime of stars and then accelerated by the explosion of stars. Heavy elements, nickel and zinc, are produced during the explosion of stars. So they come from different origins. The question is, do they have different properties? So I shared with you helium, carbon, oxygen, and lithium, beryllium, boron. A few days ago, we finished the analysis of silicon and found they belong to this class. So the fundamental question is, in the universe, does all the cosmic ray, all the elements, only have two classes or not? Very strange phenomenon. Another interesting thing is up to element number 8, they deviate from a single power law at exactly 200 GeV. Why? Nobody knows. But the question you can ask, does this continue to heavy nuclei? And so this is a letter from the American Physical Society, the editor of Physical Review Letters, and says one of the paper they decide to particularly give a citation, and mention the other paper we already commemorate in this way, including the discovery of element 117 and observation of gravitational wave. So in the eyes of physicists, we are making a small contribution. None of the experiment can be explained by the theory. And so in the American Physical Society meeting 2017, Igor Mostelenko, a professor at Stanford, and showed this graph, the current state of theory and nightmare. This is a very famous Russian printing, and shows this is a theorist confronting with new data and do not know what to do. And so let me share with you another adventure that's coming up, and that we are going to install a new cooling system on the space station October 19th this year with this satellite. This putting a new cooling system on the space station is not exactly easy. This slide comes from NASA, and this is AMS EVA crew training. We require 5 two-person EVA for AMS. They are considered to be more difficult than those completed on the Hubble telescope. This is the repair of the Hubble telescope, everybody knows. The reason is Hubble telescope was designed to be surfaced inside and out. AMS is so complex, there are very, very few interfaces that are EVA compatible. So we have a total 25 swimming pool training for the astronauts. And this is Chris Cassidy, one of the astronauts, also from MIT, and this is Kim Baldwick, and really a great engineer from NASA. So in 8 years on the space station, we have recorded more than 135 billion cosmic rays. The accuracy and characteristics of the data simultaneously from different types of cosmic ray required development of a new comprehensive model of the universe. The current theory has many parameters. You can always adjust the parameter, agree with one measurement, but the same parameter cannot explain the rest. That is the little problem we have. Most importantly, we will continue to collect data, analyze data for the lifetime of space station. Because whenever a precision instrument such as AMS is used to explore unknown, new and exciting discoveries can be made. So thank you. Dr. Paradiso, there's a video. You want to?
It's up to you, Sam. You're welcome to take a
the
couple questions.
The video takes 3 minutes and 7 seconds.
Let's do that.
People really didn't work this hard. it will require a C5 to send from Geneva to Kennedy Space Center. And this is the test in Kennedy Space Center. Make sure it fits into the space station.
Houston on the big loop. We're following you in docking mech power up, and you have a go for docking.
Endeavour copies on the big loop. Go for docking.
I still don't know how they did this.
Houston and station captures confirmed.
Incoming.
Hello, Dima. Welcome from Apollo Station. Hey, you guys wore coordinating shirts. We didn't do that. That's all right. Hello.
That's the Captain Mark Kelly.
Good. Nice to see you. Nice to see you. Welcome. Come on. Good. Good seeing you. Hello. How you doing, buddy? Hello. How you doing? All right. See you guys. All right, Taz. Get you in the video. Look at Mike. Mike. Oh, yeah, Taz.
Okay.